everybody. Good afternoon. I first thank the organizer for inviting me to present this work. I also thank the audience for being here right after lunch. I know it's hard. I guess you're wondering why. Is it interesting? And well, nowadays everybody's worried about the detection of the first gravitational wave signal. In that sense, the gravitational wave background is not the most likely signal to be detected. However, if we could do gravitational wave astronomy, and soon we will, then the detection of a background would be very interesting. It would give a lot of valuable information. For example, the detection of a contemporary background, like the one I'm going to talk about, could give us information about formation and coalescence rates of compact objects. And also the detection of a primordial background could unveil exotic processes of the early universe. So the background is actually very interesting. However, it can also be annoying. If it's an unresolvable background, it can be an obstacle to detect other signals. It can behave as a confusion noise. And binaries are known to be the main cause for this confusion noise. And that's what I'm going to talk about this annoying part of the background. So first, I will say a couple of words about what the gravitational wave background is. I will also explain how to characterize this background, how to measure it, and how to account for its resolvability, how to know what part of the background is confusion noise and what part of it is not. Then I will briefly explain the models that I use for the samples, for the systems emitting gravitational waves. In this case are binaries. And then I will present the results. I will present the expected levels of background for the whole spectrum of frequencies, not only of present detectors, but also future detectors. And I will distinguish which part of the background is resolvable and which part is not. And finally, we'll summarize and go to the conclusions of the work. So let's get started. According to the dictionary, background are the things that are behind, or the things that can be seen or heard behind other things that are closer or louder. So, for example, in this room right now, I'm the louder signal, and whatever noises right now in the audience are the background. But this definition is kind of relative, because what happens if, for example, if Sasha asks something now, or if there is some dog barking outside, then they would be the louder signals, and the rest of us, including me, would be the background. So it's kind of relative. With this definition of the background, we can be part of the background sometimes, and sometimes we are not. So I prefer to say that everything is background. So even all of us, even a big dog barking outside, all of it is background. So with this definition, we can therefore say that the gravitational wave background is made by all gravitational waves in the whole universe. And now we can distinguish different parts of the background according to different criteria. For example, as I have already mentioned, we can have a primordial background or a contemporary background. The primordial background is made by processes that happen in the early universe, like amplifications of vacuum fluctuations during inflation, or phase transitions, or cosmic strings. The contemporary part of the background is made by systems that can exist even today. For example, the coalescence of binary systems, or rotating neutron stars, core collapse supernova, etc. But there are other kinds of classifications, not only regarding the nature of the source, but also the way we can see them. In that sense, we can have, for example, a discontinuous background, or continuous, and also resolvable and unresolvable background. We will pay special attention to temporary, continuous, and unresolvable background. And we will also see that such a background does not exist in the band of present and future ground-based detectors. So now I will explain how the background is quantified, and I will also say a couple of words of how to measure, how to account for its resolvability, how to distinguish which part of the background is a confusion noise or not. So the definition of a stochastic background, which is a background that fulfills certain assumptions. This background has to be Gaussian, isotropic, homogeneous, and unpolarized. That's not the case of the background made by binary system, for example. Such a background would be fully characterized by this dimensionless parameter called the spectral function, which is basically the ratio between the density of gravitational waves in the universe divided by the critical density. Now we'll explain how to obtain this function, the spectral function, for an ensemble of binary systems distributed in the whole universe. The spectral function would be the sum, or actually the integral, of the energy emitted by one system, one binary system, multiplied by the number of systems per unit volume in a shell of infinitesimal redshift, integrated over all the shells of infinitesimal redshift in the universe. Now let's see what the continuity of the background is. Suppose now that we have a perfect detector such that in a certain frequency window we have absolutely no instrumental noise. And now suppose that we can see a signal like this one that could be a chirp signal by a binary coalescing, and we represent it in a frequency time plot like this one. So, and we represent many signals that we see during the observation time. If this here is the frequency window of our detector, of our perfect detector, then in this case we see that signals are coming in and coming out constantly, but there is silence between the signals. So before one signal enters, another one has left it. There is always a silence between them. They are separated. This background for such a frequency window would be discontinuous. However, if our frequency window was like this, then before one signal has left the window, another one has entered it. So we are constantly observing signals. In the past, some authors have made no distinction between a continuous background like this one and Gaussian background or a confusion noise. However, we can see that even if they overlap in time, signals can be very easily distinguished in frequency. So they are resolvable and they are not a confusion noise. Now let's see what the resolvability is. Again, we see the same signal in a frequency time plot, but actually that's not the way we would see a signal because we have a certain time and frequency resolution. So let's plot a grid where the pixels or the small boxes have the horizontal size of the time resolution and the vertical size is the frequency resolution. So that's roughly how we would see a signal. Now again, we plot many different signals during the observation time, and we see that at high frequencies, signals evolve very rapidly, so there is silence between the signals. It's very easy to distinguish them. However, at lower frequencies, we see that the signals evolve very slowly and they overlap in the frequency beam, so we can not distinguish them. They start to form an unresolvable background. And now we complicate it even more, and we add signals that are distant. We can think of it like we are integrating for farther and farther shares of redshift. So we do it for more and more distant signals until we have reached all the signals in the universe. And here we see an interesting picture. We see that at high frequencies, we still can resolve all of the signals, even the distant ones, because there is silence between them. there is always silence between the signals. We can resolve them. There is an intermediate range of frequencies where, and there is an unresolvable background of distant signals because they start to overlap in a frequency being, so we cannot distinguish the distant signals, but on top of them there are closer ones that can still be distinguished because they are stronger. And then for much lower frequencies we have again that if we have two parts of the background, an unresolvable and a resolvable one, the unresolvable part of the background is the one that dominates, so we can distinguish nothing. We can plot the same thing and distinguish the different regimes of the background in a more convenient way. For that I use this redshift versus frequencies plot. The blue area are the points of the observed signals. But actually this is not true. This is not the way we would observe the signals because we have to apply the redshifting of the signals. So this is how we would observe the signals because, for example, a very distant signal at high redshift, if it was emitted at the maximum frequency, which can be, for example, the frequency at the innermost stable circular orbit, it would be observed today at much lower frequencies because it's redshifted due to the expansion of the universe. So now, on top of this, we want to plot the signals that overlap in a frequency beam. So we want to know which part of the background is unresolvable. And that would be this red area here. Of course, this is in arbitrary units, but it's a way to see how it works. There is a minimum frequency and a maximum frequency where there exist unresolvable signals in the universe, and there is a minimum frequency and the maximum one where the unresolvable part of the background dominates. Even if there is a resolvable part here, the blue area, still the unresolvable part dominates over the resolvable. So this range of frequencies here is where the background is annoying. And to measure the resolvability, I introduced the overlap function, which is the sum or the integral of the time that one system spends in a frequency beam multiplied by the number of systems per unit volume in a shell of infinitesimal redshift for the redshifts in the universe until a certain redshift set. With this parameter, we can generalize the spectral function. We introduce this parameter in a certain way, and we can measure the spectral function of a background with a minimum overlap of n naught, for example, 1 signals overlapping per frequency beam. The frequency beam can be given by delta f, which can be, for example, the inverse of the observation time. So we can measure the background with the generalized spectral function. Now, I will try to convince you that there is absolutely no unresolvable background in the frequency window of ground-based detectors. For that, I will give you a simple heuristic proof of that, of the fact that there is no continuous background in that window. And the condition of unresolvability is more restrictive than the condition of continuity, because basically a background is continuous if there are signals constantly in a frequency window, in a big range of frequencies, whereas the condition of unresolvable background happens as soon as you have constantly signals in a small frequency interval, the frequency beam. So if you have no continuous background, you cannot have unresolvable background either. So I show now that there is no continuous background of neutron star binaries. So a typical value of coalescence rate for neutron star binaries is 10 to the 5 coalescence per year. That means that we have 3 coalescence every 1,000 seconds. From 10 Hz to 1 kilohertz, which is basically the frequency window of all ground-based detectors. And a binary takes 1,000 seconds to coalesce neutron sub-binary. So, naively, one could say that if we have 3 signals every 1,000 seconds, and each of the signals takes 1,000 seconds, we are going to see constantly 3 signals at any time. And thought one could say, okay, then we have continuously signals there, but that's not quite true. That would only be true if all signals were at low redshifts, at redshift 0. But what happens, in fact, is that signals are distributed in the universe with different redshifts. And now, if we consider the same example, assuming that all signals were at redshift 5, so again, we have 10 to the 5 coalescence per year, but now all the signals are at redshift 5. So if we observe them with a frequency of 10 Hertz, they were actually emitted at 60 Hertz because they are now observed redshifted by a factor of 1 plus 5, 1 plus 8, which is in this case 5. So from 60 Hertz till the coalescence, the binary needs around 8 seconds, not 1,000 seconds, 8 seconds. This interval of time is now observed as a bigger one. It's delayed. It's affected by the expansion, so we have an interval of time of 48 seconds. But still, we say if we have 3 signals every 1,000 seconds times 48 seconds, what we obtain is a number of 0.1. That's the number of signals that we will observe constantly in the band, which is less than 1. So we are not constantly observing signals. So if one does the proper calculation, one obtains that the number of signals in the frequency window of ground-based detectors is something between 0.1 and 3, and it turns out to be less than 1.
I'm not sure I entirely understand that second bullet there. The time duration of the signal really depends on the observed mass. The observed mass is blue shifted by the same factor as the frequency shifted. And therefore, if you think that it is a 1.4 solar mass neutron star, as observed, it will still take 1,000 seconds from 10 seconds. I'm not sure I understand that. I don't know what exactly you're saying. What you're saying.
I can explain it again. Maybe I didn't explain it correctly. The thing is that if we observe signals now at frequency 10 Hertz, they were emitted at 1 plus 8 times 10 Hertz. So it's 60 Hertz if we are considering that all signals are at redshift 5. We are just applying the redshifting of frequencies, as simple as that.
That's all fine, but all I'm saying is that
At the
if
mass,
the observed masses are 1.4, 1.4, starting from 10 Hertz, it will take 1,000 seconds, no matter what its intrinsic mass is.
well, I guess we can discuss about it later. Let's see. I guess the problem is that the way changes, the way the frequency, the redshift changes the frequency is much important than the time dilation. So even if you have to apply a time dilation, then the change provoked by the evolution of the frequency in time due to the redshift is much more important. But I don't know if maybe you are right. Let's take a look at that later. So that was for neutron sub-binaries, but for other binaries that could coalesce in the band of ground-based detectors, we have or smaller coalescence rates, or the times are smaller, the times that they spend there. So we would have similar results for such binaries. So we can conclude that there is no continuous background in that frequency window, and therefore no unresolvable background either. Now I will say a couple of words of what the models that I've used. That's very summarizing. Binaries are assumed to be isolated, spiraling in quasi-circular orbits and with non-spinning components. These are the mass ranges for stellar mass black holes, for neutron stars, for white dwarfs. The masses of massive black hole binaries, massive black holes range from 100 to 10 to the 10 solar masses. And these are the coalescence rates. For stellar binaries, I have taken the values of coalescence rate from these papers here. For example, for black hole binaries, I have assumed two different coalescence rates, one from this paper by the LIGO collaboration last year, and another one from this recent paper where they claim rates that are much higher than the values of the other paper. So that's why I plotted it also for comparison. The models of massive black hole binaries are the ones that have been already commented during the previous sessions. So now we'll show the results. This is the total background, which contains all the gravitational waves from all the different kinds of binaries. We have to take into account that these values here are just the average energy density of gravitational waves in the universe. It doesn't really give us information about if it's a real background or an unresolvable background or anything. We are using the spectral function to characterize a background that is something absolutely non-Gaussian and non-isotropic or homogeneous or unpolarized. So it's something that we could discuss about if it makes sense to use, or if it's valuable information what we have from the spectral function. Now we plot the continuous background, and we see that, for example, the Einstein telescope band is, as I said, free of continuous background. And however, the band of the Big Bang observer, or the SIGO as well, is fully occupied by a continuous background of black hole binaries if we assume the recent rates, which are very high, or from neutron star binaries. So there has been at least one paper that I know about the subtraction of signals of neutron star binaries from the band of the Big Bang observer. However, at that time it was not known that we would have, or that it's plausible that we could have such a huge rate of black hole binaries. In that case, it's something that could be problematic, the subtraction of so many signals. And my claim is not that resolvable signals can be subtracted out of the data, but rather that unresolvable signals cannot. And now let's see what part of this background is unresolvable. And this is what I obtained. So again, obviously the band of ground-based detectors is free of confusion noise, but the band of Big Bang observer, or the SIGO, is occupied by important part of unresolvable backgrounds. The rest of the continuous background that is not unresolvable but is continuous might be subtracted out of the data, but maybe it's not that easy. I'm not saying anything about the subtraction of signals. We can see, for example, that the background is dominated by far by white dwarf binaries and by massive black hole binaries. And we can also see that throughout the three plots, the background of white dwarf binaries is almost unchanged. So almost entirely all the background of white dwarf binaries is unresolvable. We see, for example, that the background made by massive black hole binaries doesn't enter the LISA band. This is actually the old LISA. But it will be detected by the pulsar-timing array. I can also write it that it will be detected. So let's summarize. We have seen the resolvable, we have seen the background in the entire range of frequencies of present and future detectors. We have distinguished the different regimes of its resolvability or continuity. For more details, you can take a look at my paper that will soon appear in Physical Beauty. Yeah, as I said, we have distinguished the different regimes, and there is no unresolvable or continuous background in the band of ground-based detectors. We have seen also that the unresolvable background is dominated by massive black hole binaries and white dwarf binaries, where the latter is almost entirely unresolvable. So there is still work to be done about the subtraction of signals, mainly regarding the Big Bang observer. There might be other possible sources of unresolvable background, but we can discuss about it during the week. Thank you very much for your attention.